Hello, everybody. So we move on to learning more about randomness in the data and also what kind of statistical models or how can we define it statistically in general, how can we define randomness in statistical terms, so to say. So I start this second part of that lecture with the same quotation that everything existing in the universe is a fruit of chance, a famous quotation by Democritus. So we talked about randomness in our previous lecture and how randomness or where randomness can be observed in real life phenomena. We come across several examples as well. So if a variable is random or if a variable is changing there, so remember that variable is something which is changing with time. And then if that particular unit has some randomness attached to it or has some chances attached to it, we call them a random variable. So a random variable is a numerical quantity whose values depends on the outcome of a random event. So any variable which is associated with some chance, we simply speak that variable as a random variable. We use capital letter like X, capital X to denote a random variable, and we to assign or to define the values of that random variable, that will be denoted with a lowercase letter small x. Like probability of capital X as a random variable is equal to small x with some values. There are two types of random variables: discrete random variables and continuous random variables. Well, discrete random variables take on only integer values like number of credit hours in this course, difference in number of credit hours in this term and last term. And in continuous random variables, we take on decimal values as well, like cost of books used in this term, for instance, or cost of a book used in this course, for instance, or difference in cost of books this term versus the last term. So that's how we define random variables in a discrete or in a continuous setting. So this discrimination or this division is very important to know, because mathematical structure of evaluating mean and variances and other properties of random variable depends completely on the way they are defined. If they are defined discretely, the way to evaluate their statistics will be different, and if they are defined in a continuous manner, their way of evaluating those specific measures, the statistical measures, will be completely different. For instance, if we can talk about a discrete random variable in a detail, say x, the discrete random variable takes a fixed set of possible values with gaps, with some intervals. So the probability distribution, well, the notion of probability distribution means the probabilities associated with the values of that random variable. Since they are random, there must be some probabilities associated with them. How likely they can that particular event can occur, or how likely they can occur actually. So a probability distribution of a discrete random variable x lists the values of x and also their probabilities. So we say x1, x2 up to xk, these are the values of those random variables, and each of those values have some probabilities, and we denote those probabilities by p1, p2 up to pk. There are two specific requirements for the probabilities: that they should always be between 0 and 1. They cannot be negative, for instance, and they cannot be bigger than 1. And also, if you talk about an experiment, the sum of the probabilities associated with all the values in this experiment, they should always be equal to 1. They must always be equal to 1 actually. Let's take an example to understand this mathematical phenomena more nicely. So consider an experiment where you toss a coin, where you toss a fair coin 3 times. By fair, I mean that it has both head and tail outcomes. It has 2 outcomes, head and tail. And we are interested in counting the number of heads obtained in each toss. So since you have a coin and you toss it 3 times, so x equals to 0 means there is no head. So when you toss a coin 1 time, it appears tail, you note it down as tail. You toss the coin another time, it appears tail again, and you toss the coin and the third time and it appears the tail again. So when x equals to 0, it means all of the three outcomes are tails. And when x equals to 1, it means at least one head can appear in this experiment. So you toss a coin, it appears head, and then the rest in the other two tosses it appears tail and tail. So this is one set of observation. You toss a coin again and you observed tail, and then you toss a coin again, you observed head. You toss the coin third time and you observed tail. So this is another set of observation with consisting of one head in one experiment. And similarly, the third head appears in the last position. We move on and we talk about number of heads, for instance, number of two heads in this experiment. So like two heads in the beginning and then one tail, or two heads in the ends, but and there is a tail occurs in between of those two heads, or in the first toss tail appears and then in the next two tosses heads appear. Finally, when we call or we count about total number of heads, which is 3 in one experiment, which is like all of those outcomes are head. So these are the outcomes we have gathered, or we actually by running an experiment, so to say. So now we will assign probabilities associated with those values or variables actually. So values are 0, 1, 2, and 3. Either we have 0 head or we have 2 heads, for instance, and then we move on to 3 heads in total. So now you count that in total there are 8 outcomes in this whole experiment, right? If you count all of those numbers, there are 8 in total. So the maximum frequency or the maximum number of outcome in this experiment is 8. And how many times among those 8 units it appears that you have no head actually in this experiment, and it appears only once. When you run an experiment, you observe all of those outcomes are tails. So it's like 1 because it was only one outcome and the total was 8, so we divide 1 by 8. So this is the probability associated with the event when x equals to 0. Similarly, when x was equal to 1, there are 3 outcomes. And when x equals to 2, there were 3 outcomes as well. And when x was equal to 3, there is 1 outcome. So now if you count those outcomes, you see that there are total 8 outcomes in the probability as well. Now if somebody is interested in knowing about those specific probabilities, we can evaluate them immediately. For instance, what is the probability of tossing at least 2 heads? Well, at least 2 heads means 2 or 3, right? And in mathematics or in computer sciences, when we talk about OR, we use the mathematical notion addition to accommodate that OR. So probability that x equals to 2 plus probability that x equals to 3 will give me the answer for tossing a coin with having 2 heads, or probability of tossing a coin with at least 2 heads, so to say. So we add up those 2 outcomes. Probability of x equals to 2 was actually 3 by 8, and for x equals to 3 it was 1 by 8, so the answer is 1 by 2. Again, you can come across different probabilities. For instance, there is another example. What is the probability of tossing fewer than 3 heads? So fewer than 3 heads means it can be 1, it can be 0, it can be 1, it can be 2, but not 3, right? So we combine all of these 3 probabilities together to evaluate that probability. So in this simple experiment, we notice how randomness or how probability can be assigned to a particular outcome, and how can we evaluate different chances. Even though they were not accommodated fully in the experiment, but we run an experiment in a general setting and then we look for other possibilities through probabilities. A continuous random variable, on the other hand, takes all the values in an interval of numbers. Suppose we want to choose a number at random between 0 and 1. So then there is an infinitely many numbers between 0 and 1. It can be any value. We have no restriction about the type of number we are going to pick in this interval. How do we assign probabilities to events in an infinite sample space? Well, then we look for a density curve. We call it a density curve because there are many observations or many values, infinitely many values or numbers between 0 and 1, so we make a plot. And in the end, we notice that it's a curve. We call them density curve because it specifies how dense the distribution of that particular variable is. So one of the graphical tools which we will learn is the histogram, and most often we plot the histogram to visualize the density curve of a variable. The probability of any event is the area under that curve. If you remember the notion of integration, so we utilize the integration component from the mathematical calculus to account for that density, or to account for the probability of that particular event with having that density. Some mathematical notations, you may find it hard for some of you, but for notational purposes, I tried to mention it here. So there are generally mathematical notations for continuous random variable. There exists a function we call fy. Well, that function is the probability function actually. Remember, in the discrete case, we mentioned p as the notation for probabilities, but in the continuous random variables, we will use the notation f for probabilities, so to say. We call them probability density function. Since there are so many outcomes, so many numbers involved in particular interval, so we cannot call them simple probability. They are density functions actually. They are a function of involving all the densities in that particular interval or region. There are again some conditions for those probability density functions, that they can always be positive. As we noticed, probability was positive always from 0 to 1. The sum of all the probabilities should always be equal to 1. Here again, sum of over the interval from minus infinity to plus infinity, they should always be equal to 1. And if I talk about two intervals, or the probability between two ends, so to say, so I can simply integrate the function from the lower limit to the upper limit to evaluate that probability. Cumulative density function, sometimes we also talk about it in statistics, and in both discrete and continuous case. So in a discrete case, we just evaluate the probability less than equal to a particular point. And in a continuous case, when we have a density function, we integrate from minus infinity to y, that particular function, and then evaluate the cumulative density distribution function. Discrete random variable commonly arise from situation that involves counting something, for instance. Situation that involve measuring something often result in a continuous random variable. So a discrete random variable x has a finite number of possible values, as we have noticed in a previous example as well. And probability model of a discrete random variable x assigns a probability 0 to 1 to each possible values of x. While in a continuous random variable y, it can have infinitely many possible values. So the probability of a single event is meaningless in a continuous setting. Only interval can have a non-zero probability represented by the area under the density curve for that interval, as we discussed earlier in the previous slide. So we are not in the continuous variable, we are not interested mainly about probability of a single event, rather we are interested in the interval. What is the behavior of particular variable within that interval? That is more of our interest when we talk about continuous random variable. So here is a graph of this density curve. Well, I call it a uniform density curve. It is uniform because if you notice from the point interval on the x-axis from 2 to 9, the behavior is exactly the same. The height of the whole curve is exactly the same, and that's why we call it uniform. It's uniformly behaved, it's uniformly assigned actually. But there can be different behaviors in reality. Independence, another important phenomena. Well, two random variables x and y are independent if the knowledge of y variable does not influence the result of x, and vice versa. Remember the concept of independence and dependence variable when in our previous lecture. I said that two variables are independent when one is influencing other, or other is influenced by the previous one, for instance. This can be expressed in terms of conditional probabilities. If we have dependence, then we need to evaluate probabilities through conditionals, through conditions. We assign different conditions. We say that the probability that y takes a certain value does not change if we know that x takes a value, for instance, alpha is the value. So probability of y being beta depending on x being alpha, that's what we call as that y is actually depending or independent on one another. In other words, if y is independent of x, it means that if we evaluate the probability of y being beta conditional on x being alpha, if that probability is exactly equal to probability of y being beta, it means there is no part of x comes up here in the outcome, and that's why we say that y and x are independent. If they are independent, the joint relationships can simply be evaluated through the product of individual relationships. So the joint probability can be simply evaluated through the product of individual probabilities if they are independent. The mean of a discrete random variable, well, mean we call x bar in mathematical notation, of a set of observations, and they in general they actually evaluate the arithmetic average of a variable. In mathematics or in statistics, we call them as the expected value of x as well. So how we calculate mean? Well, we know from our previous example, we know that their random variables have some values x1 to xk, and there are probabilities associated with those values. So we just multiply them together. So we multiply x1 with p1, and then we add the other component like x2 times the probability associated with that outcome, and we keep going on until we finish, like xk times pk. So we multiply each outcome with the probability and then we add them together, and this is the arithmetic mean or the expected value of that discrete random variable. Consider the same example again about the tossing a fair coin 3 times. We know the probability outcome, we know the values 0, 1, 2, 3, and we know the probabilities 1 by 8, 3 by 8, 3 by 8, and 1 by 8 associated with all of those values respectively. So if somebody asks me to evaluate the mean of that variable x, I just need to multiply each value with its probability and keep doing until I'm done, and finally I add all of those components together. So if I do so here, I see that 0 is multiplied by 1 by 8 plus 1 is multiplied by 3 by 8 plus 2 is multiplied by 3 by 8 plus 3 is multiplied by 1 by 8, and the end answer is 1.5. So this is the average of that particular experiment, of that particular random variable. And for mean of a continuous random variable, the idea is exactly the same, but since it's continuous, instead of sum we use integration, and instead of probabilities we use the probability distribution function. So we multiply each outcome with its probability distribution function and then we integrate over the range. For example, if we have a continuous random variable x with some density function, and that density function is defined over here like x squared by 9, because it's continuous, so it can be defined in that manner, and this function is valid between these limits from 0 to 3, and this function is 0, otherwise means beyond 0 and beyond 3 that function has no value. So within only the limit of 0 to 3 this function has a definition, has a meaning, has some structure. So how can we calculate the expected value of that particular variable x? So we just multiply that function with x and we integrate from 0 to 3 because that function only exists within that limit. So we just use simple calculus and then we are done with the expectation or the average of that particular continuous random variable. Variance is another important phenomena, and since mean is the measure of center, for instance, so we use the standard deviation as our measure of spread. How deviated the values are, how big the spread is among a random variable. How can we accommodate that particular property? How big is the variation between variables? So we do the same thing again. We calculate values of that particular random variable. We evaluate probabilities associated with those random variables, and then we multiply in a specific way to evaluate the variance. And the formula for variance is also not that difficult. So what we do actually here, we take the difference from each value from its mean, we square the difference, and then we multiply that particular quantity with its probability. So say x1 is the first outcome, so I take the difference of x1 from the mean, I squared that difference, and then I multiply that difference, the squared difference, by the probability associated with x1, which is p1. And then I add, I move on to second event, I do the same for second event, and I keep doing it until I'm done with the last event. So here we multiply the probabilities with the squared difference of each outcome from its mean, and then we add up together to calculate the variance. So the square root, if you take the square root of that variance, this will give you the standard deviation of the random variable. Again, for the same experiment, that coin tossing experiment, we know the values, we know the probabilities, and we are interested in knowing the variance of x. But before we know the variance, we need to evaluate the mean, since each value has to be subtracted from the mean. So we subtract each value from the mean. We have already calculated mean before. If you remember, it was 1.5. So now just subtract each value from its mean, square it, and multiply it with the relevant probability. And you keep doing this with all the 4 outcomes, and in the end you see the answer is 0.75, which is the variance of that particular random variable. For a continuous random variable, we do the same, but instead of summation we have integration, and instead of probabilities we have the function, the distribution function. So there is another famous theorem. If you are interested, you can remember that the variance of particular random variable is equal to the squared expected value of the squared random variable minus the expected value of the variable whole square. So I mean, you don't need to remember that, but if you are interested in, you can remember that. It is very useful in many ways in formulating mathematical structure of random variables. So here is another example with continuous random variable. The same example we observed before, but at that time we evaluated the mean, the expected value, but now we are mainly interested in the variance. So for variance, if I utilize that theorem, first of all I need to evaluate the expectation of x square. And the expectation of x square is nothing but the product of this inner variable, the x square, times the density function, and integrate it over the limit, which is from 0 to 3 in this case. So if I do so, I get the value of 5.4. I have already evaluated the mean. Remember that it was 3 by 2 or 1.5. So just take the square of that mean and no, I think it was not 3. Yeah, it was 2.25. Sorry, I talked about the discrete case, but it was 2.25 for the continuous case. So just square that mean and then subtract mean, the squared mean, from that value 5.4, and you will see the variance of that random variable. There are some properties of the expected value and the variance. If you are interested, you can remember them, but you don't need to. For instance, expectation of constant is a constant, because expectation deals with randomness. If something is not changing, the expectation or the average is exactly the same particular thing, because it's not changing, right? If you multiply a variable with a constant and you evaluate the expectation, it is exactly equal to the to multiplying the constant with the expectation of that variable. Similarly, addition does not change the expectation. If you are evaluating the expectation of two variables when they are added together, which is equal to evaluating expectations individually and then add up together those two variables. For multiplication, the joint is exactly equal to individual expectations if they are independent. Similarly, there are properties of variances. If something is not changing, the variance is exactly equal to 0. If you multiply a constant with a variable which is is exactly equal to the squared constant times the variance of that particular variable. This should be capital X, not small x. If you add some values or some constant to a variable, this will not change the variation because the variation of constant or the variance of constant is exactly equal to 0. For two variables, if you are interested in the variation when they are added up together, this is exactly equal to their individual variances adding up together if they are independent. And for multiplication, it's a bit complicated formula. If you need, you can remember that. But this formula also holds if x and y are independent. So in this lecture, we talked about some mathematical notations about randomness and discrete and random phenomena, continuous random phenomena, some mathematical expression about mean and variances. In a similar manner, we can proceed for other statistics as well, like skewness, kurtosis, median, if you're interested in. So my point was here to give you a brief overview about mathematical notations. We will not be dealing with mathematical notations a lot in this course, but it's good to be familiar with them. So see you next time, and we will come across with more interesting topics and more serious topics related to this course. Thank you very much.